In the last video, we introduced this notion of integers modulo n for a given n. So this is an algebraic structure which has n elements. We denote them by 0, 1, 2, 3 until n minus 1. This structure is denoted as z by nz. That's our notation for this structure. And as we said, in order to distinguish the integers from the integers modulo n, we can write these ones with bars. We can do it whenever there is some possible confusion. So in this structure, I have this operation plus. And how do I add two numbers? So I say a modulo n plus b modulo n is the same thing as a plus b all modulo n. This plus here is the usual plus for numbers, for integers. And this plus here is the plus of this structure. Now, if a plus b is greater than n, then a plus b bar doesn't appear here. And if I want to write it as an element which is here, I just subtract n. Same thing, if a plus b is smaller than 0 is negative, so it does not appear here, so I can add n and I fall on an element of the same form of which I just listed. And the same holds for the product. So I have product of integers modulo n defined by a modulo n multiplied by b modulo n is just a times b usual multiplication modulo n. And again, as for the plus, a times b modulo n is one of these elements, even if a times b is greater than n. Because I can always subtract n's without changing the elements. And I subtract n enough times to fall on an element between 0 and n minus 1. It's the same as saying I just divide a times b by n and I take the remainder. And a times b modulo n is the same as the remainder modulo n. So as an example, we have, for example, the elements modulo 7 with the plus and multiplication. The set itself I represented by the integers between 0 and 6. So those are 7 elements. I can put those bars here or not. And then I have the plus and the multiplication. And if there's confusion, I put bar. So how do I multiply two numbers? For example, if I take 4 times 5 is the same thing as 20. But if I want one of these elements, I just divide by 7 and take the remainder. So this is 6. 20 equals 6 modulo 7. And 6 plus 6, for example, is 12. But this is the same thing modulo 7 as 5. Now, the last question of the last video was, I have an element and I want to know if it's invertible, modulo n, and I want to calculate the inverse. How can I do it? For example, modulo 7, if I take the number 3, by what can I multiply 3 to get 1? I realize, in fact, that 3 times 5 is 15, which is the same thing as 1 modulo 7. So 3 is invertible, the inverse is 5. In general, how can I know that an element is invertible? And how can I calculate the inverse? Something I can say immediately is that 0 is never invertible. And this for any n. Because for any a, 0 times a is always equal to 0 and would not be equal to 1. I can write a theorem about this question. So take any n. Let n be a natural number. Or in fact any integer, which is not 0. And let x be any element of z. Then x is invertible modulo n if and only if the greatest common divisor of x and n is equal to 1. So if and only if x and n are coprime or relatively prime. Well, for the proof, when do we say that x is invertible modulo n? We say this if and only if there is another integer y such that x times y equals 1 modulo n, or x times y is congruent to 1 modulo n. It's the same thing, which means that x times y minus 1 is some multiple of n. Now, when is this true? By rewriting this, I can write x times y minus k times n is 1 for some k in z and some y. Now, for a given x and a given n, when could I find such a y and such a k such that this equation is true? Well, I know that if the greatest common divisor of x and n is indeed 1 by the Bezout identity, I can find, in fact, some a and b such that a times x plus b times n is 1. Now I have this identity because I can just take y equals to a and k is negative b. So b is negative k. This shows that if x and n are relatively prime, then x is invertible modulo n. Now reciprocally, if the greatest common divisor is some integer which is just greater than 1. Now in this case, this identity cannot be satisfied because the d here is a divisor of x and it is a divisor of n. So whatever y and k are, d must be a divisor of x times y minus k times n. So this number cannot be 1. So we proved our theorem. A corollary of that, for example, is that 3 is not invertible modulo 12 because they are not relatively prime. But 5 and 7 and 11 are all invertible modulo 12. Now, how do we calculate the inverse? We just have to find the coefficients which appear in the Bezout identity, and we have the inverse immediately. And we have an efficient algorithm to find those coefficients, which is the Euclidean algorithm for finding the greatest common divisor. It's an efficient algorithm, so it runs quickly. So we can give an example. So find the inverse, so exercise, find the inverse of 43 modulo 107. I can write it, for example, find 43 to the power minus 1 in the ring of integers modulo 107. And I can add a bar here. So how do I know it's invertible? First of all, I have to check that they are coprime. 43 and 107 coprime. Are they coprime? Well, yes, they are coprime because in fact 107 is a prime number and 43 is not a multiple of 107, so they must be coprime. So by the way, it's an important remark. If you take here a prime number, so everything except 0 is invertible in this structure. And by 0 we mean, of course, the class of 0. So it consists of 0 and the multiples of this number. So I know I can find the inverse by solving for the Bezout coefficients. So I start my Euclidean algorithm. I write 107 is 2 times 43 plus 21. Now I divide 43 by 21, so 43 is 2 times 21 plus 1. And okay, I got the 1. This is the greatest common divisor. In fact, if you run the Euclidean algorithm for one step more, you get a 0. So because you'll have to divide 21 by 1, and the remainder, of course, is 0. And the greatest common divisor is the less non-zero remainder. By the Bezout identity, I can write 1 as something times 107 plus some other thing times 43. I can do it here in 2 steps. The first step, I use this identity to write 1 as 43 minus 2 times 21. And now in the first step, I get rid of the 21, writing it as a combination of 107 and 43. So for the 21, I write 107 minus 2 times 43, which is negative 2 times 107 plus 5 times 43. Now on the integers in z, I have this identity 1 equals negative 2 times 107 plus 5 times 43. But if I'm looking at the things modulo 107, so all this is 0. It's the same thing as 0. And I can write that 5 times 43 is 1 modulo 107. So what's the inverse of 43? It's 5. And the set of integers modulo 107. And this algorithm runs quickly. In fact, here it ran too quickly. We had just 2 steps. The Euclidean algorithm finished just in 2 steps. But in general, it runs quickly. Let's do another quick example. So find the inverse of 8. I can write it this way. Modulo 37. So in the structure of integers, modulo 37. And again, here I have a prime number, so I'm sure that this number with the 8 are relatively prime, and I can calculate the inverse. The inverse exists. So I start with the Euclidean algorithm, then I find the Bezout coefficients, and then I'm done. So I divide 37 by 8. It's 4 times 8 with a remainder of 5. And then I divide 8 by 5. 8 is 1 times 5 plus 3. 5 is 1 times 3 plus 2. 3 is 1 times 2 plus 1. I got to the 1. So yeah, which is, of course, the greatest common divisor. And now I write 1 is 3 minus 2. With this equation, I get rid of the 2. I write 5 minus 3. 3 minus 5 minus 3, which is negative 5 plus 2 times 3. And now I get rid of the 3 using this equation. I write it 8 minus 5. So the 1 now is minus 5 plus 2 times 8 minus 5, which is 2 times 8 minus 3 times 5. And with the last equation, I get rid of the 5. So I write the 5 as 37 minus 4 times 8. So I have now 2 times 8 here, and in the second term I have 12 times 8, so it's 14 times 8 minus 3 times 37. Good. So now the Bezout identity says that negative 3 times 37 plus 14 times 8 equal 1. And this identity is true in Z, and then just integers, we know. But now if I'm looking at the things modulo 37, so this is 0. And thus I have that 14 times 8 equals 1, which can be written that 14 is in fact the inverse of 8, modulo 37. So what's the inverse of 8? It's 14, modulo 37.